Okay, recording should have started. Okay, so hi guys, let's start the session now. So today the session is about your quiz 2, which is basically covering the column loads and also the column design. Yeah, and what we call the simple frame construction. Okay, so I should have given you 3 files. One is this one, the practice file. The second one is this one, the reference. So basically all the formulas that is required for quiz 2. And the other one is the steel design table, which gives you the section properties. So during the quiz, right, I suggest you to first thing is bring the reference sheet because you need the formulas. The second one is to print and bring the cross section table, because unlike quiz 1, right, they wouldn't give you the table. You must actually look at your own table. Let me see if I have it. Yeah, it's basically I don't know if you can see, but it's this book. Yeah, so it gives you all the um oh, maybe I'm blur first. Here. So you're using my camera. Yeah, so basically you need to bring this table into the quiz too. Okay. The pages to print I've sent in the group already. Okay, then another admin stuff. Yeah, so this cheat sheet, right? I'll only give until like quiz 2. Yeah, but yeah, the one that I give is enough for quiz 2. But for finals, I'm selling it for $10. Just to give you some info. Okay, but anyways, yeah, let's start the session now. Okay, so let's start with the review first from the previous topic. So this is the exact same slide, but I'll just repeat. So if you want to design a structural member, right, you need to start with getting the loading first. Get the loading, and then after you get the loading, right, you need to factor the loading based on what is required. So there are 2 cases. One is ULS, which is the ultimate limit state. The other one is SLS. But for column, I think now we focus on ULS first. 1.35 and 1.5. Those are the factors. And then after we gain after we put partial factors into the loading, we need to do structural analysis. Basically, we need to find the shear bending or axial force on the structural member. Okay, basically find the NED, MED, or VED. For columns, we are concerned with NED and MED. VED is only for beams usually. Okay, and then after you've gotten the loadings, then you choose the structural member. So for this one, they either give you the structural member to check, or you need to choose your own structural member. And then after you check after you select the structural member, you do the design checks. If all the design checks pass, then it's okay. Yeah, it passes lah. If it fails, then you need to redesign. Okay, but for this course, again, if it fails, right, just write check fails. You don't need to redesign, okay, because it takes time. Okay, so again, here are the partial factors for, again, we are interested in ULS for unfavorable conditions. Okay, means the loading is not helpful for the structure. So it's 1.35 and 1.5. Okay, and then just to review again, the loading path. So again, if we stand on the slab, the loading goes to the slab first. Okay, then from the slab, it goes to the beam. Then from the beams goes to the column. So today we will learn how to transfer the loads from the beams to the columns. Yeah, because last time we did this one, right? We did tributary loadings on slabs. So what we've done is we converted the loading on the slab, which is in kilonewtons per meter squared. We have converted it into this thing, the UDL or point load. Yeah, or triangular load. Okay. I hope you still remember this because okay, just to review, if you have a beam which is directly getting load from the slab, it becomes a UDL. But if you see, like for example, this junction, right? If there's a junction, so if we plot this one. If you plot BDF, okay, BDF, then simply supported because it's a steel structure. Yeah, because there's a junction in BDF, right? Here, there's a point load at D. So the value of the point load at D, right, is actually the reaction on beam, like this beam. Okay, it's the reaction on D. Okay, so I hope y'all still remember. If y'all forget, then review from the first session. Okay. Okay, so now let's go to columns. So for columns, right, just to make you aware, there are a few types of cross sections. So we have the I-beams. You can use UB, but usually you use UC, which stands for universal column. Universal column. This is the most common section used for columns, for steel at least. So if you go to your cross section table, right, you can go to you can search for universal columns. I don't know if you can see that, but yeah, it's there. Universal columns. So usually, yeah, for this one, right, if you are given, for example, UC 356 times 406 times 364 something like this. If you see this UC, right, then you go directly to the universal column section. Okay. Okay, next we have channels, angles, which is not really common to use. These stuff also not really common. Now we have this CHS, SHS, and RHS. So this one is another common section. So HS, right, stands for hollow section. So hollow section. Then C stands for circular. S stands for square. R stands for rectangular. Let me check the table. I think they just say CHS. So if the questions give you like CHS, SHS, and RHS, you know where to find it in table. Okay. Usually for Singapore, right? For Singapore, okay, let me put it here. Okay, for Singapore, usually we use hot rolled sections. Hot rolled indicates the manufacturing method. So for steel, there are two kinds of manufacturing method. So manufacture, there's the hot roll. Basically, the section is crafted in when it's hot, lah, basically. The other one is cold form. You can read about this online, but usually for Singapore, we use hot roll. Okay, I'm saying this because the cross-section table, right, actually has two, which is again a hot roll and cold form. So for your case, right, just use hot roll, okay, for all the time. Okay, so that's the types of steel sections for columns. Okay, there are four common again: UC, CHS, SHS, and RHS. Okay, so let's continue on. So there are the major and minor axis. So this is another concept that you need to know. This is especially for RHS and UC. Okay, so for UC and RHS. Okay, so usually we label a section, right, according to their strong and weak axis. So we call the strong axis YY. We call the weak axis ZZ. Okay. This is important because buckling usually happens in the ZZ axis. So you need to know which one is ZZ, which one is YY. Okay. So how do you read ZZ and YY? We use the right hand rule. Okay. So right hand rule, right hand thumb rule, the thumb rule to be exact. So YY, right? So if you put your fist like this, right? So the thumb is the axis, the fingers, right, are the rotation direction. So YY means rotation in this axis, in the YY axis. Okay, so this is MYY or MY. Okay. And then for Z, right, it's along this axis. So this one is MZ. Okay, so this is a common mistake because people usually flip the two. Okay, because they thought the YY means that way lah. No, that's not the case. So use the right hand thumb rule. Okay, or just thumb rule in short. If you notice, right, for I beams, YY, right, is always parallel to the flange. So if the flange is this way, your YY is also this way. Okay, because the section, right, is stronger in this direction. Okay, in this direction rather than this direction. Okay, so again, how do you know YY is you follow the flange. You follow the flange. ZZ, right? You follow the web. So this one is you'll get used to it lah. Okay. Like after a while you get used to it. And even intuitively, right? Intuitively, MY is stronger than MZ. Like this shape is stronger this way. Okay, rotating it that way. Okay, so even though they might like do this, right? Sorry. For example, the top view, right? They give you this way, right? YY is still this. This is Y. Sorry. This one is still YY. This one is ZZ. Okay. So yeah, this one is something you need to get used to. So it doesn't matter if they give you this way or this way, YY is always parallel to the flange. Okay, YY is always parallel to the flange. So don't get confused on the orientation. For RHS, okay, for RHS, let me draw it here. Okay, imagine this is the RHS. It's a rectangle, hollow section. Yeah, hollow section means the inside is empty, by the way. Okay. So for this case, right, YY, this one is YY. Because again, it's stronger in this direction. Okay, it's just logic. You can try that out. Okay. This one is the ZZ. Let me label it with another color so you're not confused. So this one is ZZ. Okay, that's ZZ. So again, it doesn't matter the orientation. The YY is always parallel to shorter the shorter side of the RHS. Okay. Okay, again, this one I'll change the color so it's quite clear. YY and ZZ. Okay, so that's for UC and RHS. Okay, not all cross sections have a major and minor axis. So not all cross sections. For example, CHS and SHS. If you look at the section, it's quite straightforward. Why? Because it's symmetrical in the XX and YY direction. So there's no strong and weak. Okay, they have the same capacity. Okay, so I hope this is clear. Again, this is something quite straightforward, but it's really important. Okay, it's really important. So don't get this wrong. Okay. Okay, now we go to the fun part. So this one is some theory that you need to know lah. Okay. Yeah, but again, all of this is actually quite common sense if you've learned this. Okay. Okay, now let's go to the beam to column load transfer. Okay, so if you how to explain that? Okay, so if you remember, right, your beam is usually like this. There's a reaction here, and there are like loadings like on top. Okay, so the reaction forces, right, where does it go? It must go to the columns. So something like this. Okay, the reaction force goes to the column. Here I have another column like this. However, in most cases, right, the beams cannot be exactly in the center of the column. So the center of the column is here, right? The center of the column is here. If you notice the connection, right? Of course, you cannot connect the beam in the middle. Okay, you must connect it slightly off center. Okay, so the reaction forces, right, get Okay, ideally, right? Ideally. So for the ideal case, the reaction force of the beam is transferred directly to the middle of the column. Okay, so both of these are okay. This one is NED. This one is the reaction by right. But in most cases, again, where where do I put this? Yeah, okay. So for most cases, your reaction, right, gets transferred here off center. So imagine this is the reaction forces. Okay. So we call this the eccentricity. Okay, the beams are eccentric to the columns. Okay. So we usually label it as E, as the letter E, small letter E. So like this length here is the eccentricity of the beam. Okay. So if you notice, there's a moment arm. So there's a moment induced on the column. Okay, there's a moment, which is R times E. So it's that simple. Okay, so R times E. R is the reaction, E is the eccentricity. So we call this moment, right? We call it the nominal moment. So the moment due to eccentricity, we call it the nominal moment. Okay, nominal moment. I'll explain why it's called the nominal moment later, soon, in the next page. Okay, but anyways, all you need to know, right? The eccentricity causes a moment. Okay, and this needs to be taken care. So most cases, the columns, right, are attached to not only one beam, but a few beams. So in this case, right, there are two beams going to the making the YY. Yeah, so this is the YY, right? So these two light blue color, right, makes a moment about the YY direction, while the darker blue, right, makes the moment about the ZZ direction. Again, how do I know YY and ZZ? You must look at the column itself. So again, YY is parallel to the flange. So this is YY. Okay. So yeah, as in here. Okay. So there are two moments induced. So how to calculate the moment induced, right? Again, it's just logic. You imagine a seesaw. You imagine the seesaw. So if there's yeah, okay, seesaw. Okay. So the total moment, right, is basically the moment induced by one column, sorry, one beam compared to the other beam, and you just minus the effect. Okay. So for example, we give this. Okay, let's imagine this R1. This one is R2. Then the ZZ one, right? This one is, let's say, let's use another letter. Let's say this is P1. This one is P2. Okay. So P2. So basically, the eccentricity at the moment at YY, right? So MY. So MY is just R1 times E1 minus R2 times E2. So it's that simple. And usually we are only interested in the magnitude. Okay, so plus minus doesn't really matter. Okay, just take the difference of the moment. Similarly for MZ, so MZ is just the magnitude of P1 E1 minus P2 E2. Okay, basically the eccentricity of each reaction forces. Okay, again, this one is just logic lah. Okay, so this one is a seesaw lah. Okay, so again, the beam transfers two things. One is the axial force. The other one is the bending moment. Okay, actually, yeah, I forgot to mention the axial force. So My, right, is based on the eccentricity. So R1 E1 minus R2 E2. Then for MZ is P1 E1, P2 E2. Then you just take the difference. But how about the axial force? For the axial force N, right, basically, again, it's just quite simple because all the loadings must go into the columns. So the loadings by the four beams, right, must go to the column. So N is just R1 plus R2 plus P1 plus P2. So basically take all the loadings, but also you take the loading from above, okay, from the above levels for N. Okay, let's call this N, so plus N. Okay. Okay, this one I'll label it NED, so it's clear. So NED. I'll also go label this MYED. And the other one is MZED. Okay, so if you notice, right, MYED and MZED only cares about the current level, while the normal force, it also takes account on the levels above. Okay, so this is something to take note. Okay, I'll show it again later. Okay, but okay. So now that we know about the nominal moment, right? Now the question is, what's the value of E? What's the value of the eccentricity? So for Eurocode 3, we take this assumption of 100 millimeters from the column face. Okay, not from the column center, it's from the column face. Okay. So let me emphasize this, it's from the column face. So for an example, right, for I-beam, right, for a YY, so YY again is this axis right here. So this one is YY. Okay. So load transfer is here. This is the beam. This one is the top view, by the way. Okay, so it's 100 millimeters from the face of the column. So this is the distance, like 100 millimeters. Okay, but again, if we take eccentricity, right, we must take it from the middle of the column. So it's 100 millimeters plus, in the case of the I-beam, is h over 2. Okay, that's why MYED here is R multiplied by h over 2 plus 100. Okay, so I hope that's clear. For ZZ, is the same 100 millimeters from the column face. So again, here you see, right, it's 100 millimeters from the column face. But then eccentricity you must take from the middle of the column. So you add this tiny TW divided by 2. So TW means the thickness of the web. Okay, this part, thickness of the web. So you just take half. Okay, that's why in this case, MZED is R times TW over 2 plus 100. So using the same logic, right, I hope you know how to find RHS. Okay, for example, like this. So this is the middle of the column. So this one is B. This one is H. Okay, so for RHS, your MYED, right, is just R multiplied by 100 plus this length, right? H over 2. So H over 2. While your MZED in this case is R multiplied by 100 plus B over 2. Okay, in millimeters. So it's that simple, okay? So the theory is always 100 millimeters plus this tiny distance to the middle of the column. Okay, and it depends on the section. Okay, so I hope this one is clear. Okay, so far so clear, right? So if you have any questions, please ask me through the chat or just unmute yourself, yeah? But so far, I think it's quite straightforward. It's just common sense, but it's something that you really need to know. Okay, so here's the not so common sense. Okay, so here's the simple frame constructions. Okay, this one requires you a little bit of your structural analysis knowledge. Okay, so what is a simple frame construction? Yeah, in simple terms, basically you make all the joints to be pins. Okay, so if you see here, right, if you look at this picture, oh, this one is actually fixed, but okay, it's okay lah. But basically, the assumption is the connection between the beam to the column is all pin. Okay. So this implies something. So now let me give you two cases. So one is a fixed beam like this. So the other one is a simply supported beam. Okay, so simply supported is under the simple frame constructions because all the joints are pins. So this one is simple frame or simply supported. The other one is a fixed one. So this one is, we usually call it, I think it's a continuous one. So, or rigid frame, rigid or, so rigid frame or continuous construction. Okay, so now if you plot your bending moment diagram, right? So imagine this is your bending moment diagram. So this is M, this is X. Let me copy that for the other case. So this one is your bending moment diagram. So for the rigid frame construction, your BMD should look like this. It should look like this. While for simple frame construction, it should look like this. So the main difference between the two, right, is for rigid frame constructions, since the end is rigid, right, or fixed, it has a bending moment. Remember, right, for a fixed one, they have this, then also the bending moment. While this one, it doesn't have a bending moment, just these two. Okay, no bending moment. So this implies the BMD, right? If you see in the edges here, there are moments. Okay, there are moments. So M1 and M2. While for this one, there are no moments at the edge. So what does this mean? This means that this beam, this fixed beam, right, transfers the moment onto the column. Okay, I repeat, this M1 will be carried by the column. Okay, so while this one, it doesn't have a moment. Okay, so for rigid frame, there's a moment. For simple frame, there's no moment transferred to the column. So now if you notice, there are two sources of your moment on the column. So if this is your beam, this is your column. Okay, so this is beam, column. Okay, it's a very simple drawing, just lines. Okay, but basically, the moment, right? The moment on the column is caused actually by two things. So moment, right? The moment on the column is actually caused by what we call the fixed end moment of the beam plus, actually not the fixed end moment, just end moment. So end moment of the beam plus the nominal moment. Okay, so that's actually the MED. So for the end moments, it's actually this one. So these are the end moments. Okay, let me draw that. Okay, so those are the end moments. The nominal moments are these ones, the one that we have covered just now. Okay, those are called nominal moments. So yeah, again, the total moment is caused by the end moment plus the nominal moment. However, for simple frame constructions, now you can see the benefits, right? If we assume a construction to be simple frame. Okay, there's no end moment. End moment is 0. Okay, end moment is 0 for simple frame constructions. So we just need to take care of the nominal moments, which we have covered just now. Okay, so just take note that this MYED and MZED doesn't come from the PMD. Okay, it doesn't come from the PMD because for simple frame constructions, we assume the BMD, right? The edge of the beams, the end of the beams, the moment is 0. Okay. Yeah. So the moment just comes from the eccentricity. Okay, so I'll just put here eccentricity. This one is from BMD. Okay, then what's next? I think. Wait, I forgot what I want to say. Wait, simple frame constructions, beam column. Oh yeah, oh yeah, oh yeah. So for these ones, right? Rigid frame construction or continuous construction is usually common in reinforced concrete structures. Okay, this one is usually for reinforced concrete or RC. So this one will be covered in another topic. It's in CV 3011. Okay, while this one is common for steel structures. Okay, for steel structures, which is CV 3012 lah, the one that we're doing now. Okay, just to give you an idea on where to use which. Okay, because for concrete, right, it's usually cast up together, like it's like flush to each other, so it cannot rotate. So that's why we assume it's a fixed joint. While for steel, right, steel we usually use this kind of what we call fin plates. So these fin plates, right? So fin plates, they are usually able to rotate. That's why we assume it as spin. Okay, this is just for your fun fact lah. Okay, so I hope this one is clear. Moments are caused by two things, end moment and nominal moments. So here are the pros of simple frame constructions. You can read it yourself. Okay, it's simpler to construct. It's like easier to analyze. Again, just now. Yeah, yada yada yada. Okay, all these. Okay, sorry. Okay, so I hope this one is clear lah. Now we go to, I think this is the last theory, right? Yeah, this is the last theory. Okay, so lastly, now let's talk about moment distribution on stiffness. So if we go back to this drawing, right? Like this set of beams, right? This set of beams is not only connected to one column, it's actually connected to two. Okay, so if you look at this diagram, this beam, so this red beam, is actually connected to the bottom column and also the top column. Okay, it's not connected to the bottom only or the top only. No. Okay, so if there's a moment in this case, right, by the beam. Okay, imagine there's a moment by the beam. So the question is, does it go to the bottom column or does it go to the top column? Okay, wait, let me drink. Okay, so actually, right, the moment by the beams are carried by both the columns, both. So if this is M, right, if this is M, so some part of M, right, so some ratio of M, let's say alpha. So alpha M is carried by the bottom column, while the top column carries 1 minus alpha times M. Okay, it's just a ratio. So the total must be 1, right? So that's why, yeah, just use ratio. Okay, so yeah, it's also feasible in this diagram here. So if you notice, right, the bottom beam, right, carries this much moment. Okay, that's the moment. Yeah, you see this line. So this one is alpha M. While this tiny portion, right, is carried by the BMD of the top column. And this one is 1 minus alpha times M. So the total is M. Okay, just for you to know, the BMD of a simple frame construction should look like this. It's like Z, like that, okay? Okay, just so you know. So if you see it inside your software, right, you know which one is right, which one is wrong, okay? Okay, so now the question is, what's alpha? So what's the ratio? So the ratio is based on this one. It's based on what we call stiffness. So the stiffness of the column is EI over L, okay? EI over L. So sometimes they give the stiffness, sometimes you need to find yourself, okay? EI usually is the same for top and bottom column. Okay, E, right? there's a fixed value. There's a fixed value for E. It's 200,000, right? Megapascals, right? I think this one is for the E of steel. Then for the I, right, depends on the table. So C table. So as long as the column, right, has the same cross section, then I should be the same. So usually L is the one which is the main factor, okay, of the ratio. Okay, so M upper, right, is just the stiffness of the upper column divided by the total stiffness of the upper and lower column. So if you look at this diagram, this is the upper column. So this is upper, this one is lower. Okay. So yeah, you just find the stiffness of the bottom column, so K lower. So it's just EI over L lower. While this one you just find K upper. Okay, so straightforward again. Okay. So yeah. So it's quite simple. Okay, but for the Eurocode 3, also there are also very nice assumptions. Okay, so you can assume that the top and bottom column you can split half-half. Okay, so if the moment is M, the top and bottom column receives half M. So that's also possible. But you must satisfy this following condition. Okay, the stiffness ratio must be less than 1.5. Okay, so if you take the ratio, right? If you take the ratio, this and this should be less than 1.5. Okay, must be less than 1.5. Less than or equal. Less than or equal. Okay, if the stiffness ratio is 1.5, then you must do the, yeah, you must do this one. It's the stiffness ratio. Okay. So yeah, it's quite easy, right? You'll see later in the examples. Okay, so now let's go through the theory first. Okay, lastly, we have this thing called the combined check. Okay, so remember just now, right? Columns are subjected to bending moment and axial force. Okay, so bending moment, so MED and NED. Okay, mostly NED, but MED also have. Okay, let me rearrange. Okay, NED is the primary one. Okay, this one is the primary one. Okay, how to explain? So these two, right? If you remember MOM, is both are under normal force. Okay, normal force. While VED, right, is usually under shear force. Sorry, normal stress and shear stress. So if you notice NED and MED, right, these two should interact with each other. Okay, it interacts with each other. Okay, so when we design for a column, we must consider this kind of interaction, and this is what we call the combined check. Okay, it's to consider the interaction between the axial force and the moment. Okay, so when you check, right, there are a few checks that you need to be done. One is the axial resistance check, including buckling. One is the bending moment. Second one is the bending moment resistance. Lastly is the LTB check. Okay, so the first one is to check NED. Okay, the first one is to check NED. The second and third, right, is to check MED. Okay, so the first one is to check NED. The second one is to check MED. So once you check it individually, right? So firstly, right, you check NED against buckling and axial buckling. Okay, so that's the first check. And then the second check, right, you must check MED against bending moment resistance. And then you need to check MED against LTB resistance. So in total, 3 checks. Okay, by right, 3 checks. However, after you've done it individually, right, you must combine it in this one formula. Okay, this is the combined check. Okay, this is the combined check. So just plug in the formula, make sure it's less than 1. Okay, so very simple, right? For simple constructions, the coefficient is 1 and 1.5. Okay, if the construction is not simple, so meaning there's like some fixed joint or something, The coefficient is something else, but this is outside the scope already. Okay. So yeah, I think that's all. So yeah, so NB min RD, right, stands for, I think, buckling minimum resistance design. So yeah, like buckling resistance of the column. So when we say buckling, right, if we mention buckling and nothing else, it refers to axial buckling. Okay, axial buckling. Okay. Then MBRD, right, refers to the LTB resistance. So LTB, right, of course, it refers to the lateral torsional buckling. So if you notice, right, there are two kinds of buckling here. There's the axial buckling, there's the LTB. Okay, if we mention buckling, it refers specifically to axial buckling. So axial buckling is the one which is caused by MED, where LTB is caused by MED. So this one is there should be a clear distinction between the two. Don't mix the two. Okay, we will see later. The design process of LTB and axial buckling is very similar. So that's why the distinction between the two, right, must be really, really clear. Okay, so I think that's all. So yeah, that's all for theory. I think I covered a lot already. So now let's go to the practice questions. So as usual, I won't go to the design yet. I will go to the loading first, because you must get the correct loading to do the correct design. Okay, so the principle is still the same. Okay, so let's look at this. So it's actually the same question as the first session. Okay, but now instead of the beam, we are interested in the column. Okay. Wait, okay. So let's look at the questions. So now the columns are this one: UC 305, 305, 240, and then you are given the characteristic dead load of this and live load of this. So as usual, we must find the design loading. So the design loading, so WULS, so it is 1.35 multiplied by 4 plus 1.5 multiplied by 2. This one should be 8.8 because I didn't change the question. Okay. But let me double check with the calculator. So 1.35 times 4, 1.5 times 2. Oh, it's 8.4. Okay, oops. Okay, so now we have the design loading. So now let's say we are interested in, let's do column B. Okay, let's do column B. So this column here. So let's do column B. Okay, so how do you find the loading on column B? So remember, we have two cases. Sorry, not two cases, two things that we need to find. One is the axial force, one is the bending moment. So if you notice, column B is connected to two beams. Okay, let me label this C and D. So column B is connected to the beams BD and AB. So we need to find the loadings on those two beams first. Okay, so let's do BD first. So beam BD. So if you remember beam BD, right? We need to check first whether there is a ULS or point load. So in this case, we have the ULS. So this ULS. So if we draw the beam, right, it should look like this. So this one is D, this one is B, then this is W. So W here is 8.4 times 1.5, right? Yeah, 1.5. So times 1.5, so that's what? So 8.4 times 1.5, you get 12.6 kilonewtons per meter. Then the length of it is 10 meters. So the reaction on B, so reaction on B by beam BD, okay, let me label it RBD. RBD is 12.6 divided by sorry, 12.6 times 10 times the length first divided by 2. Again, divided by 2 because it's spread into D and B. And why can we divide by 2? Is because the beam is symmetrical. The loading is also symmetrical. So we can divide the loading to 2. So 12.6 times 10 divided by 2, you will get 63. Okay, so that's beam B, D. So now let's go to beam AB. Okay, because again, we need to consider beam AB because it's connected to B. Beam AB. Okay, beam AB, right? Again, we need to check UDL and point load first. Well, we have a point load here at Y, right? We have a point load here. So if we draw it, it should look like this. So this AB, we have point load 4 meters and 3 meters. So we have this 4 meters, 3 meters. Okay, so what's the loading? The loading, right? We must use tributary area. Okay, again, the point load, where does it come from? It comes from here and comes from here. Okay, so the point load is 8.4 multiplied by this length. So it's 3.5, right? So because this is 2, this is 1.5, so this is 3.5. Okay, so 8.4 times 3.5 times the length, which is 10, divided by 2. Why we divide by 2? Because the loading, right? This blue area, it will be split to 2. So going to X and going to Y. Okay, again, this one is just just a recap. So we will get what's the value? So 8.4 times 3.5 times 10 divided by 2. You get 147 kilonewtons. Yeah, I think that should be correct. Looks correct. Okay, now we find the reaction on B. Okay, so this is A, it's B. So we find the reaction on B. Okay, we don't take A lah because we are finding the column at B, right? So let's call this RBAB. Okay, this is just some random notation I I made lah, but as long as you know what it means, okay? So RBABD, right? Sorry, RBAB, right? You can take moment, right? So take moment about A. So take moment about A. So you will get 147 minus 147 times 4 plus your RB times 7 equals to 0. So your RB is equals to 147 times 4 divided by 7. You will get 84 kilonewtons. Yeah, 84 kilonewtons. Okay, so now we have the loadings, right? So if we draw it in 3D, if this is your column, so AB, right? Beam AB is 84 kilonewtons, the reaction. So this is AB, right? So this is B. This one is 2A. This one is 2D. So here is 84. Here is 63. Okay. So, oh, and then you need to look at the orientation of the beam. Okay, because we have primary and secondary axis. So let me redraw this. This is actually like this. Okay. You don't need to draw in 3D lah if it's your exam. I'm just drawing it here for your visualization. Okay, but practice it without drawing the 3D. Okay, it should be pretty obvious actually. Okay, so it looks like this. Yeah, so it looks like this. Okay, so this one is clear, right? So if you look at this one is YY. Then this one is ZZ. Okay, again, if you look at this top view, the beam looks like this, right? So this one is YY. This one is ZZ. Okay, so practice the YY and the ZZ thing. Okay, so NED, what's NED? So NED is just 84 plus 63 because those are the reaction forces. And by right, do they indicate any top column? No, right? Okay, so the top columns, right? So it's the N above, right? So it's a normal force above, but in this case, we don't have. So this one is just 0. So in the end, you will get 84 plus 63, 147 kilonewtons. Okay? So that's NED. And then for MEDY, I think it's quite clear now. MEDY is just 84. Sorry, not 84, 63. Okay, because YY is going that way. Wait, yeah, it's shorter, right? Then anyway, no. Oh, last loading. Yeah, so 63 multiplied by the eccentricity. So for YY, this portion is h over 2, right? So h over 2 plus 100. It's always 100, right? Okay, so yeah, because I guess this is YY, right? So this is the distance. So it's h over 2. Okay, so 63 times h over 2. So h is 325.5 divided by 2 plus 100. Again, this one is kilonewtons. This one is millimeters. So if you want to make it kilonewtons meter, right? This one you need to multiply by 10 plus 10 negative 3. So you will get 63 times 325.5 divided by 2 plus 100. You divide everything by 1000. You will get 16.6 kilonewtons meter. So if you notice, right, the moment value, right, shouldn't be that big. Okay, typical moment values in BMD, right, is around the hundreds, like 100 or 200 kilonewtons meter. But for nominal moments, it's usually less than 100. Not always, but usually, because the moment arm is very small, right? So yeah, your value shouldn't be very big. Okay, that's how you check if you're right or wrong. Roughly. Of course, you cannot like know exactly, but roughly you can guess. Okay, it's an educated guess. Okay, so MEDY is similar. So MEDZ is similar. So 84 times. So you go to the table. So practice using the table from now on, yeah. So go to this one, go to TW. So this one, 23. So TW divided by 2, 100, 84, 23 divided by 2 plus 100 times 10 negative 3. So you get 9.3 or 9.4. So if you notice, right, it's very, very small. It's less than 10 even. Okay, so that's how you find NED, MEDY, and MEDZ. Okay, the rest of the questions you can try yourselves. However, I can teach you a trick, okay? I can teach you a trick. So let me copy the page. Okay. Let me delete this. Okay, this is especially useful. Okay. Especially useful in practice, especially when you've gotten to your IDP, integrated design project, or during your intern. Okay, but this is something that you might want to know. So this one is only for NED, NED of the column. Okay, it doesn't work for MED, but works for NED. For NED of the column, you can actually use tributary area loading. Okay, tributary area. The logic behind this, right, is because all the loadings from the slab will eventually end up in the column. Doesn't matter which beam it takes, it always end up in column. Correct? So let me write it down. So it doesn't matter which beam it takes. Loading always end up at the column. Okay. So for example, right, if you look at this, right, so the loading will be applied on all this area. Okay. Remember that it doesn't matter which beam it takes. It doesn't matter which beam it takes. So we can quote unquote ignore the beams. Okay, we ignore the beams. So we just focus on the column. So 1, 2, 3, 4. So we just divide the slab area into equal parts. So the distance between these two columns, right? The midpoint is around here. This column and this column, the midpoint is here. This column and this column, the midpoint is here. This one and this column, the midpoint is here. Okay, so you just divide it into like this. And that's it. That's your tributary area for the columns. So basically, it means this column B, right, will receive the loading on this area. This column, last time I labeled this C and D, right? So column D, right, will receive the loading on this area. C will receive from this area. Okay, and then A will receive from this area. So that's it. So very simple, right? So just take the midpoints within the columns. It doesn't matter the beams, then you just find the area. So we can check lah. So NED is this one is 5 meters, right? This one is 7 divided by 2, so that's 3.5. Okay, so our loading just now is 8.4. Okay, so 8.4 kilonewtons per meter squared times 5 meters times 3.5 meters. You will get 147 kilonewtons. So if you check, right, 147 with the one just now is 147 as well. Okay, so that's a very fun trick to do. Okay, and it's actually very useful because moments, right? Again, nominal moments are usually very small. So in initial design, we usually ignore the moments first. We just find the axial force because axial force is much more critical in most cases. So yeah, so that's why we usually use this method first, the tributary area, because it's very, very fast. Okay, ignore the beams, take the midpoints. Okay, like this one, if you see, right, if you do the beams one by one, right, it's really, it's quite crazy lah. So usually just take like this, done. Only for NED, okay? Only for NED. Because for MED, right, you need these reactions from the each beam. Okay, that's why you cannot use the tributary area directly. Okay, that's the problem with beams. Okay, so for MED and MEDY and MEDZ, you must actually do the beam calculations one by one. But for MED, if you have no time, just do this. Okay, so yeah, that's all. So let's take a break first for 5 minutes, and we'll continue with the questions, with the design questions. Okay, so yeah, so let's continue at 11:11. Okay, lucky number. So 11:11. Okay, so yeah, see you after the break. You can ask any questions now also, so I'll accept any questions. Okay, let me pause the recording. Okay, let me continue the recording now. It's 11:11. Okay, so let's answer the two questions asked. So first one is, where do you get 3 to 5.5 for my? So this value, right? Okay, oops. Yeah. So this value, right? Remember, this one is the reaction times eccentricity. Okay. So the eccentricity is 100 millimeters. Is from the face, right? So plus this value. In this case, it's h over 2 because it's in the y direction. So this value is h over 2. So you get h from the table. Okay. Let me once again let me bring this table. So again, you must print this one and practice using this. Okay. You should get the h from the table. Okay. So yes, that's where you get h. The next question, right? For the stiffness ratio, so this one is talking about this. So for the I, do we use IY or IZ? So that's also a very good question. The answer is very simple. Because remember, right, bending moment goes in two directions, YY and ZZ. So the stiffness ratio, we just use IY for Y direction, IZ for Z direction. So yeah, so that's it lah. So IY, you use it for MY, IZ, you use it for MZ for the stiffness ratio. So yeah, so that's it lah. But usually, right, again, once again, the top column and the bottom column, usually they use the same section. The same section, we have the same IY and IZ. Okay, so usually I is not looked at unless the section is different. Then you need to consider IY and IZ separately. Okay, so I hope that's clear, huh? Okay, so we've done tributary area. So now let's go to the, again, design question. Okay, so now we have this. So this is a typical question. It's a because if you build a building, right, usually it's more than one story. It's usually multiple stories. Okay, no, multiple levels. Okay, so now let's read out the question first. So, oh, it's recording, right? Oh, yeah, recording. Okay, so we have a 3-story office building. It is designed as a simple non-sway breeze frame. So again, you see the word simple here. So it's a simple construction. Wait, give me a second. Okay. Okay, non-sway and breeze, right? You can read it yourself, but it means it doesn't, the column doesn't have shear. Okay, that's what this one is a sway frame. So the whole building moves like sideways. That's what a sway building is. But that's outside the scope of the, what's it? Outside the scope of the lecture. Yeah, so yeah, just take it as it is. Okay, so it means it doesn't do this one sway. Okay, then they give you the grade of the steel S275. Then you are given the column 254 by 254. You're also given the loading, which is 1,900. Okay, that one is from the upper columns. Yeah, 1,900 is from the upper columns. From the upper stories, actually. It's a total loading of the stories plus the columns. Okay, so that's 1,900. Something, something, something. Yeah, that's it. Okay, so part one, right? List 3 advantages of using simple frame construction. So this one, you can refer to the theory just now. It's on the slides above. You just find yourself, okay? So let's continue to the design part. Okay, so okay, show that the proposed column is adequate. So it's a very simple question. Okay, but remember, right? We have 3 checks to perform. So for part B, right? By right, we need to do first things first is always the axial buckling check first, or axial check. So NED. Then we have 2 checks, right? Is the bending resistance and LTB. Okay, LTB. So this one is usually MEDZ. This one is usually MEDY. Yeah, something like this. Okay, so now let's do the check one by one. Okay, so just to give you context first, let's imagine it in 3D as usual. So from the loading from the upper stories, right, is 1,900. Okay. Yeah, the total loading from the upper stories is 1,900. You can see it here also. So 1,900 applied on the centroid. And then the reaction of the beams they have given us. So it's um quite good. So now we have 120 acting here, 30 acting here. Okay, so we can find the loadings. Okay, so let's find the loadings. Again, we have three loadings: NED, MED, MED. So let's find one by one. So NED is straightforward. It's 1,900. But remember, you need to add the current columns as well. Sorry, the current level as well. So you need to add 120, add 30. Because the loading, like this 30, right, also goes to the column. This 120 also goes to the column. Okay? So you need to add both. So you'll end up with 2,050, I think. Let me check my calculator first. Yeah, maybe where's my calculator? Okay, so 1,900 plus 120 plus 30, yeah, 2,050 kilo newtons. Now we find MEDY. Again, you must be able to find it from the picture. So you see, right? This one is YY. Again, using the thumb rule, you will have it like this. Okay, that's YY. Then for ZZ, it's this way. Yeah, that's ZZ. Okay. Actually, let me draw the arrow this way. Okay, just to match the loading. Okay, so MEDY is 120 times. Again, this one is H/2, right? This one is H/2. This one is assume 100. So 100 millimeters plus H/2. So this one you need to refer to the table. Again, the table that you refer to, right, is the column. Okay, again, the one that you refer to is the column. Okay, because again, it goes back to the theory. The moment arm should go to the center of the column from the edge. Sorry, from the reaction force. Okay, so the H here is the H of the column. So it's not the H of the beam. Be careful. It's not the H of the beam. Don't go to the wrong section. It's a column. So if you refer to the column, I put it here, 254, 254. Sorry, 254, 254, 89. 254, 254, 89. So it's this one. So you go to H, you get 260.3. Later we will use this also, 10.3. So let me just write it down. So 8 is 260.3. TW is 10.3. Okay, let's go back. Okay, so this one is 260.3 divided by 2 times 10 negative 3. Then MEDZ is this value, 30 times 10.3 plus 2, sorry, 100 plus 10.3 divided by 2 times negative 3, 10 negative 3. Okay, so just find the values. 260.3 divided by 2 divided by 1,000, you will get 27.6. And for the other direction, you will get 3.15. So it's a very small value, but it's normal. Okay, again, it's just nominal moments. Okay, now we have these three values. We just do the check. So again, as usual, check is very it's very quick. Just follow the steps. You just know, you just need to know which steps to follow. Okay, so you can open this. Oh, wait. Before that. I forgot. This value is not yet distributed. Okay, I forgot. This one is not yet distributed. Now let me label this MY. This one is MZ. Okay, so remember we have the distribution, right? So we are checking column X. Okay, we're checking this column. We're checking this column. Okay, so if you notice, the length is 3.5. This column, the length is 2.8. Okay, so we need to find the ratio of stiffness. Let me move this down. Okay, so top column and bottom column, they have the same section, right? I think they have the same section. Let me see. Yeah, I think they never state. Okay, we show them the same. Okay, so I put it inside the cheat sheet in this page. So you see, right? Just go to simple frame constructions. Then you'll see NED, MYED, MZD. Okay, then these are the calculations just now. Then we have this one. Calculate the upper and lower column stiffness. And then you take the stiffness ratio. Okay. So upper column. So K upper is EI divided by L. The upper column length is 2.8. So divided by 2.8. Then K lower or X, right? Which is the one that we're interested in, is EI divided by, I think it's 3.5. Yeah, 3.5. Okay, so 2.8 and 3.5. Now we check the ratio. Okay, so ratio, K ratio is equals to EI divided by 2.8 divided by EI divided by 3.5. The EI cancels out. So you will get 1.25. Okay, so if you notice, this value is less than less than 1.5. Okay, so if it's less than 1.5, okay, by the way, the ratio taken should be bigger than 1 before you check 1.5. Okay, so usually we take the lower length on top because it gives 1.25, which is bigger than 1. Okay, so before you check 1.5, right, you must make sure it's bigger than 1 in the first place. Okay, that's why I put it here. But anyways, yeah, let's go back to here. If the ratio is less than 1.5, then you can split the moment into half. So if we go back here, okay, so based on this, therefore split half. Okay, so we have MEDZ, MEDY first, and MEDZ. So this one is half times 27.6 and 3.15. Wait, is it 3.15? Yeah, it is. Okay. 27.6 divided by 2, you will get 13.8. So it's even lower if you even notice. Then 3.15 divided by 2, you will get 1.57 or 1.58. Okay, so that's the value that you're going to check. Okay. is the one which has been redistributed. Okay, let me just put it here. Okay, so we are done. Now let's go to the checks. I almost forgot. I keep forgetting for some reason, even last year. But okay, anyways, let's continue with the checks. Okay, so let's go to the new checker because I think LTB and bending resistance you know how to do, right? So now let's go to this one, the NB min RD, the design action. Sorry, the buckling resistance. So in my cheat sheet, it is located under compression members because axial load, right? Compression. Okay. So there are two checks for compression members. We have the cross-sectional resistance, which is this value. So A times Fy divided by gamma MO. Then also we have the axial buckling check. Axial buckling check. So axial. I'll just put this in a parenthesis. Okay. So if you notice, it's the same A times Fy divided by gamma. But now we have this reduction factor. Okay. So that's the only difference. Usually we check both actually. We check both, but usually, right, buckling is always more critical. Okay. Buckling is usually more critical than axial resistance, but we check both. Okay, so axial resistance first. So axial resistance. Okay, so what's the check? So we just need to calculate NCRD. So step one. So NCRD is A. Again, A, you need to go to the table. So if you see here, right, this is the table. We are dealing with 254, 254, 89. Okay, this one I explain a bit on the table. So again, look at my camera. So for each section, right, there are two pages. There's one page on this, one page on this for the same section. That's why in the screen share right now, there are two tables because they are located on two different pages. So be careful. So for one section, there are two pages dedicated to it. At least I think only for UB and UC. For hollow sections, I think only one page. But for I-beams, right, two pages. So be careful. So for the first page, it's usually about the geometry. For the second page, it's usually about the sectional properties. Okay, just to let you know now. Okay, so you see, right, the first page, they will have H, B, T, W, T, F, C, all those. For the second page, they have the radius of gyration, which is I, you will see later. Then second moment of area, which is big I, elastic modulus, WEL, plastic modulus, WPL, all this, and cross-sectional area. Okay, so the thing that people sometimes get wrong, right, is actually the area, which is the simplest thing, right? But because they are tricked with this, okay, it's not the surface area. Okay, it's not the surface area. Be careful. The one that we use is the area of section. Okay, be careful. Don't get it wrong. Okay, so for this one, we use 113 cm squared. Okay, so 113. Usually, I like to change it into SI units. So you just go to this converter. So cm squared is 10 to the negative 4 in SI units. And then what's the formula again? Times Fy. So Fy here is 275 times 10 negative 6. Sorry, megapascals, 10 to the power 6. Divided by gamma m0. So gamma m0 here is 1. So let's calculate the value. What's the value? So 113 times negative 4, 275, divided by 1, you'll get, by the way, let's make it kilonewtons. So negative 3. Okay, so you'll get 3008 kilo newtons, which is way bigger than NED. What's NED? NED is 250, 2050. Okay, so this check is okay. Okay, so that's actual resistance done. It's that simple. Okay, it's very fast. Okay, next now let's go to actual buckling resistance. So actual buckling now. Okay. So first things first, you need to determine the effective length LCR. So find LCR. So LCR. Okay, so if you notice, it's dependent on two things. One is the length between the restraints. One is the connection details. So you need to go to this image. So you go again, it's a non-sway building, right? So you go to this. If sway, you go here. But we're talking about non-sway. Then you check the boundary conditions. So for this case, it's pin-pin, right? It's pin-pin. So the LCR is simply 1.0 times L. Okay, 1.0 times L. The common cases, right, is usually pin-pin or fixed pin. So it's either this or this, pin fix. Okay, but in this case, it's pin-pin, so it's 1.0 times. So the length just now is 3.5. So it's just 3.5. Okay, so LCR done. Wait, let me see. Yeah, actually it's stated in the question as well. So effective length factor may be taken as 1. Okay, and in the next question, actually you can notice if the joint C is replaced with a fixed joint, then that's fixed pin. And that will affect the LCR. Okay, so these things you need to pay attention. So the boundary conditions. But now we're doing B. So let's do it. Effective length to be 1. Okay, 1L. So yeah, 3.5 meters. Yeah, just double check 3.5, but just 3.5. A bit paranoid because you get the loading or the first step wrong, right? The rest is wrong. So be careful. Okay, step 2 is calculate this or this. So NCR is the critical, I think the Euler's critical load or whatever. The first one is just a factor. Usually we take this only. Okay, this one you can ignore if you want. The second one is just an alternative formula, but it's easier to go this route usually. It's easier to go this route. So let's just calculate that. So epsilon is square root of 235 divided by, just now is 275, right? So let's take that. The square root of 235, 275, I think it's 0.92. Yeah. Oh, I memorized it. Okay, but anyways, 0.92. Then you calculate lambda L. Okay, this one is L, by the way. It's not 1, it's lambda L. Okay, so it's lambda L. So in this case, you will get 93.9 times epsilon. In this case, you will get 0.92. So 93.9 times 0.92, 86.4. Okay, so that's the factor. Okay, now let's continue on. So step 3, calculate lambda, this thing. So again, there are two possible formulas. One is based on NCR. So you see this one is NCR. The other one is based on this I. Okay. Again, we ignore this because it's a longer route because NCR, right? Unit E, unit I. So that one is quite quote unquote annoying lah. Yeah. Because a lot of things to consider. Okay. So this one you can ignore. Just go to this route. So lambda L. So LCR, which is 3.5 divided by small I. So this small I, the small I here refers to the radius of gyration. So this is something that you need to remember. Okay, radius of gyration is small I. So now the question is which one to take, YY or ZZ? The answer is you take the axis which is more susceptible to buckling. Most cases, it's ZZ. In most cases, it's ZZ. So in this case, it's 6.55 centimeters. Let's make it SI, so 10 to the power of -1. Okay, you can, sorry, -2 centimeters, okay? -2. Okay, so it's here. Okay, I will explain it later when to use IY. Should I do it now or? Okay, we finish the formula first. So times 1 divided by, oh sorry, this is not lambda L. This one is lambda bar. Okay, so lambda L just now is 86.4. 86.4. So therefore you will get 3.5, 6.55. 2 times 1, 86.4. 0.618. 0.618. Okay, this one usually is less than 1. And I think it's supposed to be less than 1. I think you can double check. Okay, now before I continue, I'll explain first when to use IZ and IY. So usually, okay, again, I use axis more prone to buckling, more prone to buckling. Usually it's ZZ. So usually ZZ. Okay, but this is not always the case. So when is it not the case? It's because, for example, you have this, right? I think you can see this in 2018 past paper, I think. I forgot the exact year. Okay, but now consider this. So this is your column. So usually, right, it's more prone to buckle this way because that's the ZZ axis. Okay, it's the weak axis. However, if you put some restraint in the middle, so you put restraint here, right? For example, you put restraint here. Okay, only in the ZZ direction. Okay, only in the ZZ direction. Okay, you put restraint on the ZZ direction. Then this implies that your column in the ZZ direction, it won't bend the whole length. So when it buckle, it will buckle half like this, half like that. Okay, while in the YY direction, it still buckles the whole way because there's no restraint in the YY direction. Okay, so for ZZ direction, your L, or LCR actually, your LCR now becomes L over 2. While YY, your LCR is still L. And buckling, right? If you remember MOM, your buckling, right, usually happens, sorry, it's more prone for buckling when, one, the section is weaker, or two, the length is longer. Okay, in this case, YY, the length is longer, but it's stronger. So if you notice, YY is longer, but stronger. This one, it's weaker, but shorter. So which one is more critical, right? If the answer is we don't know. Okay, we don't know which one is more critical. Okay, if the length is longer and it's a weaker section, then we know which one is weaker already. But in this case, right, if it's restrained in YY direction, we don't know which one is weaker or stronger. So in this case, you must do two cases when you check for buckling, for actual buckling to be exact. You must check with two cases. One is the IZ, one is the IY. So you need to do two checks for the buckling because we don't know which section is more critical. So I hope that clarifies. However, in this case, right, if you notice, in the question that we're doing, there's no restraint, right? So imagine this is your section. There's no restraint in the YY or ZZ. So this YY, ZZ. There's no restraint in both. So they have the same L. So YY and ZZ, same L. LCR lah, actually, LCR. So this one, we factor out already. We don't need to check which length is longer or whatever, because LCR is the same, because there's no restraint. So the column will buckle the whole way anyways, both in ZZ and YY directions. However, now we can know which one is the weaker section. Okay, the weaker section is always ZZ. And that's why in normal cases, we usually use ZZ in normal cases. Okay, so the only case where we use IY is when there's a restraint in the weaker axis. Then we need to do two checks, one with IY, one with IZ. Okay, so that's a long theory section. Yeah, but just for you to know, okay? This one just for your information. For this course, it's usually ZZ lah. But in 2018, it came out where it's restrained like this. So who knows, huh? Okay, and in real applications, right, it's usually, yeah, sometimes there's this case also. So it's good for you to know. But anyways, let's continue on, because the rest, right, is just follow the steps. Right? Okay, now we're at step 4. Okay, we're at step 4 now. So now select appropriate buckling curve based on HP and T. So see next page. So the next page is this big table. Okay, so we just go to the appropriate section. So we have a rolled section, which is an I-beam, you can see from the picture. And then we need to find H over B, right? Okay, so now let's find H over B. So H over B is, let's go back here, 260, 256, 260.3, 256.3. So if you notice, it's roughly 1. Okay, but for exactness, let me calculate. It's 1.01, 1.02. Okay, so this one is definitely less than 1.2. Okay, so rolled section, H over B is less than 1.2, TF is less than 100, and it's buckling about the ZZ axis. Okay, let me write it down. So TF, what's TF here? TF is 17.3. So this one is definitely less than 100. And ZZ axis. Again, how do we determine YY and ZZ? Yeah, you follow this. Okay, follow the assumptions. So this one, buckling curve. What's the buckling curve? C is S275, right? So buckling curve C. Okay, remember this one is 275. Okay, so if you're making your own cheat sheet, right? This is just a disclaimer first. If you're making your own cheat sheet, just take note that the buckling table is different from LTB. Okay, just in case you're making your own cheat sheet. So the buckling curve here, right? If you notice, right, it's different from where is it? It's different from this buckling curve. So yeah. So this one is LTB. The LTB buckling curve is different from the axial buckling table. So this is the table for axial buckling. So for buckling curve C, you will get alpha equals to 0.49. Okay, so now we have that. So what's next? Let me see. So yeah, it's the typical calculation. So you find phi. So what's that? 0.5. times 1 plus alpha. What's alpha? Alpha is, oh, it's below 0.49. Times lambda bar. What's lambda bar? Is 0.618. Then minus 0.2 plus lambda bar 0.618 squared. Therefore, you will get 0.5, 1 plus 0.9. Okay, so you will get 0.793. Okay, now let's add another page. Okay, so you get phi. Now you get, I think it's lambda. Oh no, it's chi. Chi is equals to 1 divided by 0.793 plus square root of 0.793 squared minus lambda bar, which is 0.618 squared. So this value should be less than 1. So let's check. 1 divided by 0.793 plus square root 0.793 squared minus, yeah, it's a long calculation. 0.775. Looks all right. So because this is less than 1. Because chi is supposed to be a reduction factor, so it must be less than 1. Okay? By its name. If it's bigger than 1, it's not reduction, it's amplification. Okay? This one is reduction factor. Just so you know. Okay, so now we find MBRD. Okay, so it's 0.775 times area. Again, what's the area? Actually, it's the same. Yeah, it's the same as the one before. Okay. Paste, you get this. Okay. So the value is 0.775 times 113 times 7. You get 2,408. 2408.3 kilo newtons. Correct me if I'm wrong. Let me check once more. Yeah, looks correct. What's the NED just now? Oh, 2050. So barely, so bigger than 2050. Okay. So, okay. Okay. Oh, it's a long track. So now you need to do LTB and bending resistance by yourself. I'll leave it to you. Okay, bending resistance. Okay, I'll leave this to all of you. I'll just show which one is which. So LTB, I think it's quite famous. I think you know which one it is. So LTB is this one with the MCR, the infamous, yeah, this formula. So you need to find this MBRD. Okay, I'll just write it down. So LTB, so MBRD is XLT WPLY FY divided by gamma M1. So that's LTB. Then for bending resistance is the other one. So bending resistance is this one. Okay, so in the first page, you see this first page, you go to this one, bending resistance check. Then calculate the bending ring moment resistance MCRD. So this one is MCRD, which is WPL. This one is a bit different. This one is WPLZ times Fy divided by gamma M0. So why is this one Z? Because LTB, right, is already used to check. So LTB is already used to check MEDY. Okay. So the remaining one is MEDZ. Okay. The remaining one is MEDZ. That's why we use WPLZ. because z is applied on the z direction. So of course you need to use the WPL of the z direction. Okay. So yeah, just to let you know. So this one again, you do yourself, you do yourself. And also there's a combine check, right? So combine check, you do yourself also. Okay. I think there's a solution on the website, on the C Club website. You can refer to that. Okay, so combine check. Okay. So I think with the remaining time, right, we have 10 minutes. I'll just explain some theory. Okay. So usually, right, sometimes you are not given the number of story. Okay, you are not given the number of story. Okay, yeah. So now, for example, right? Okay, for example, right? Let me make my own case, right? For example, you have a column. So let's say this is your column. Okay, this is your column. Yeah. Okay. So now let's say you are given this info. Let's say you are given this info. For one floor, for one story. Okay. Yeah, the keyword here is one story, right? So for one story, these are the loadings. Okay, these are the loadings. For example, this is 20. This is wait, it's too low. 150. This one is 200. Okay, for example, this is for one story. This is the loading on the column. Now the question is, how many stories can the column support? That's a common question, both in the quiz and also in real life. Because if we're designing a high-rise building, right, we need to determine the size of the column. So what we usually do is we find the loading for one story first. Then we multiply by the number of stories. Understand, right? So yeah, so in real life, right, this applies for real life also. So in this case, remember that columns are most critical. So columns are most critical to axial buckling. So the keyword here is axial buckling, right? So usually you must compare the loading with axial buckling. So what's the resistance for axial buckling? Is the one that we've calculated just now. It's NBRD. So calculate, also find NBRD, the buckling resistance. Okay, that's usually your first step. Second step is find the loading. Sorry, find the loading. So find loading of column. So if this is column X, for example, this column, oh no, this, let's give this column M. Okay, column M. Okay, so now imagine this. This is the building. Okay, imagine this is column M. Okay, this is story 1, story 2, and so on, right? So how do you find the total loading? So NED, again, NED is here, right? NED is the loading here, NED. Okay, so NED is just 150 plus 200, right? 150 plus 200, which is the loading by the beams and by the slabs, arguably. So 150 plus 200 times N. Okay, N is the number of stories. So where N is the number, so number of stories above column M. Okay, so that's the loading of the column. Okay, now we have the have the axial buckling resistance. Now we have the loading of the column. So what do we do to find the number of stories? We just use a inequality. So the loading of the column must always be less than the resistance, correct? So what's the loading of the column? In this case, it's 350 times M. So this value must be less then the resistance. Let's say, for example, the resistance is, let's use 10,000, for example. Okay, let's use 10,000. So therefore, N must be less than 10,000 divided by 350. Okay, this one just example, for example. For example. Yes, therefore, you will get, what's 10,000 divided by 350? Well, hello, 28 point. Let's actually let's reduce it. Let's make this 5,000. 10,000 is too big. Okay, let's make it 5,000. So you'll get 14.2, 14.3. So N is, what's N? Remember, you must always round down. Okay, no matter what, you must always round down. So this case, it must be 14 stories. Okay, round down, always round down. So 14 stories above column M. So by right, if you count the ground floor, so by right, or 15 stories, including ground floor. Yeah, so this is just for example. But the calculations, right, you must actually do yourselves, using the, again, using the nominal moment, no, sorry, not nominal moments. It's the one before. Yeah, it's basically these calculations, and also the buckling check. Okay, and then one more thing. I think I've written it in the cheat sheet. I just want to emphasize. Where is it? Here. So for NED, right? For NED, you must consider the current and upper stories. But for the moments, you only consider the current story. Okay, this is just to emphasize the one just now. I think I've labeled it here. Okay. Oh, it's not. Okay, never mind lah. But yeah, basically, right? If you have this, this kind of building, right? For the moment, you only consider this beam. Okay, for the moment. But for the NED, you consider everything above as well. Okay, you consider everything above and the loading on the current column. Sorry, loading on the current story. Okay, that's why here NED, right, is this value times N, because you need to calculate the number of stories, like this number of stories N. Okay. Now let me emphasize it's ongoing. Something like this. Okay, so lastly, before we end, I just want to bring light to this also. So, because I think there are some misconceptions also on this thing. Okay, so sometimes they will give you a question in this way. Okay, you have a column here. So the column is this section, 5.9. By the way, I'll extend a bit by around 5 minutes just to finish this. Okay, it's connected to two beams. This is the first beam. This is the second beam. So the question is, how do you get the loading? Okay, for this one, right, it's a beam subjected to UDL. So let's focus on AC first. So on AC, right, they have two reactions, here and here. So the reaction of AC is 60 kilonewtons per meter. So 60 kilonewtons per meter times 3.3, the length, then divided by 2. Divided by 2 because there are two reaction forces. So the load is spread equally. And because the beam is symmetrical as well. So that's the loading from beam AC. Okay, 60 times 3.3 divided by 2. So you will get 99. Okay. Then for beam AD, you have two reactions as well, one here and one there. So the reaction was the reaction. So our AD is 50 times 2.9 divided by 2. So 50 times 2.9 divided by 2, you will get 72.5 kilonewtons. So the loading will be 99 here, and then 72.5 here, and then the normal calculations apply. Okay, just one thing to take note, right? The eccentricity, for example, we do this, right? The eccentricity is h over 2 plus 100. Common mistake, it's quite funny, but some people use this as the h. They use this as the h. This one is not h, huh? Okay, that's not the h. The h is, again, is this value. Sorry, the h over 2 is this value. It's based on, sorry, it's based on your column. Okay, so here, h is 260. Okay, actually, by right, you need to check the, check this. Sorry, yeah, so where is it? 260. Okay, so it's 260, it's not 2.9. Okay, it's not this length. This length is only useful to find the loading. Okay, just for you to take note. Okay, but eccentricity, we still use this value. That's why I put this question here, because just in case. So it's similar to this, the eccentricity is h over 2 plus 100. Okay, so E is equals to h over 2 plus 100. This h is 260. It's not the 3.3, yeah. It's not this. It's not this. Okay, I think I missed something, but I forgot what it is. just one last thing. Wait. Yeah. Oh yeah. Okay. One last thing. Okay, this is the last thing I'll say, and that's it. Okay. So I put it inside my cheat sheet, but I just want to emphasize. Okay. Oh, there we go. So for CHS, SHS, basically all the hollow sections, the LTB resistance is equals to the moment resistance. Basically saying for hollow sections, you don't need to check for LTB. Okay, you don't need to check for LTB. So if we go back to the question just now we have three checks, right? The axial buckling resistance, LTB check, and bending resistance. Okay. For the next question, this one is SHS, right? So there are three checks that you need to do. One is axial buckling. That's the first check. It's always the axial first because that's the most important check. Second one is not LTB. Okay, it's not LTB. Remember, LTB, no need for hollow sections. So you need to check the bending resistance of YY and ZZ. So this one saves time actually. Okay, so these are the three checks you need to do for hollow sections. Okay, so I'll just emphasize here. LTB, no need for hollow sections. You just need to check according to their bending moment resistance. Okay, so both you just need to use, you can go back to the first page. You just need to use this for hollow sections. Okay, the WPL, again, if it's YY, you use WPLY. If it's ZZ, you use WPLZ. So yeah, that's everything for columns, including finals. So yeah, I'll be accepting any questions until 12:10. Just don't forget to fill in this feedback form very quickly. Yeah, you can scan the QR code, and while you scan it, yeah, you can ask questions as well. So yeah, thank you guys for coming or watching. Okay, let me screenshot the participants first for attendance. Okay, I think that's all. Let me wait. Yeah, are there any questions? If there are any questions, I'll be accepting. Okay, so yeah, I'll be stopping the recording after the questions. Okay. Yeah, so just to give you some context, I guess, what's like for finals, right? If you're making your own cheat sheet or you want to prepare in advance, right? Because there's a lot of things in Steel, right? It's actually quite easy, the design checks, but it's a lot of content. So yeah, I'll just give you an overview. So okay, this one we have covered. This one is the cross-section classification. And there's also this table which gives you the FY value. Okay. And yeah, that's for this one. So we've covered this. Restraint beam, the shear and bending, right? We have learned this. The bending resistance, shear resistance. LTB, we have covered this as well. Then this one is not covered in quiz 2 and not covered in quiz 2 and quiz 1. So this one is the web buckling check. So it's this kind of checks. Okay, so if you're having a concentrated force on a beam, how will it react? So this one is not covered yet. Okay, but it's in finals. Then you have tension members. So basically, if you have a member, yeah, if you have a member which is pulled, how does it how do you check this? Okay, so that's tension member. And yeah, there's the normal tension angle. There's the normal tension member. There's also the angle. So yeah, then you have what else? Yeah, angles, channels, dissections. This one we've covered. B split. This is not yet covered. Then also the connections, which is the bolts and weld. Where's the weld? Welds, and that's all. So we have 4 more topics, I think. Yeah. So yeah. So yeah. So 4 more topics, like if you want to make your own. So yeah, but column, right? Column is fully covered already. Yeah, just need to familiarize yourself with these few pages. The compression members, simple frame, and yeah, that's it. You can ignore this. You can ignore this page, by the way. This one is the also for columns, but this is for general. General means the support can be not simply support. Sorry, it's every other construction besides simply construction. Simple construction. So the joints, right? The whole building can be like anything. So this is the general check. It's more complicated. You can see you can see the factors here, KYY and KYZ. There's also KZY and KZZ. So you need to follow this. Wow, this is a monstrosity. There's a lot of calculations to be done. Yeah, but the concepts are actually the same. The concepts are actually the same. Yeah, so yeah, for this table, sorry, this page you can ignore. I just put it here because it's in the lecture notes. The one that you really need to focus on is the simple frame constructions. Okay, because that's the most common construction for steel. Okay, just everything simply supported, everything pin. Okay, so if there are no questions, then yeah, I guess I'll end the session now. So thank you guys once again for coming. Yeah. So see ya. I'll stop the recording now. So.